For lesson 6, part 2, we're going to continue our exploration into inverses of functions. We wrestled with switching domain and range, switching the x and the y to solve for the other variable, etc., etc. And here essentially is what we're going to continue. We're going to continue with example 3. We did this last time, and I'm just going to kind of jog your memory here. We had this situation where we had the opposite of x squared minus 2, and it gave us this parabola that then we found the inverse of. So we kind of made a table of values, we sort of explored that idea, and we found that the inverse is simply a recipe for writing the domain becoming the range, and the range becoming the domain. And so we end up with this function that is, this graph that is reflected over the line y equals x. All right, so it's reflected over the line y equals x. And this is our new relation, this is our new inverse, which in this case is not a function, right? But the exploration was this. The original domain was the x values were from negative infinity to positive infinity, and the range, the y values, were members of the set from negative infinity to negative 2 inclusive. When we're talking about domain and range of the inverse, the domain is the former range, but now it's the x values that go from negative infinity to negative 2 inclusive. And the range was the former domain that is now y values that go from negative infinity to infinity. All right? This is not a function. It fails the vertical line test, womp womp, but that doesn't mean that it's not a defined relation. All right? And so one of the things that we want to highlight then is how do we articulate that? So the inverse of x, the inverse of f of x is going to be written like this. The inverse of f of x is how we're going to read this. We put that same f that we use for function with a -1 exponent, which is, it reminds us of that multiplicative inverse, it reminds us of that additive inverse, and so we use this notation. F with an exponent of -1 means the inverse of the function of f. All right, so with that, we want to kind of perpetuate this conversation. And this might be a little bit of a struggle, especially if you wrestle with domain and range, right? It's been many months since we last engaged with that. We spent a couple months learning from the beginning of the year until about the middle of the second quarter last semester, focusing on domain and range of everything that we dealt with. We dealt with domain and range. So here we have a new relationship. This is called a square root function or a radical function. And what we're doing here with this is we are trying to understand what's the domain and the range of this. Well, we're really limited because the x values can't be all real numbers. We can't take the square roots of negative numbers. So x plus 1, this radicand, the thing under the square root, has to be bigger than or equal to 0. We can take the square root of 0, we just can't take the square root of things less than 0. That's where we get into imaginary numbers, but we can't graph that on an xy plane. There are negative numbers, there's no I values in our traditional xy graph. All right, so with that being said, x has to be bigger than or equal to -1, which means the domain, the x values, will be from -1 to positive infinity. The range, on the other hand, is dependent on how far to the left can this go and what is going to be its lowest value output. Well, I can only get a square root that is going to equal 0. All right, the square root of 0 is 0, and it's not going to go any lower than that. And so the y values will go from 0 to positive infinity. Now we can confirm this by graphing this relation in our grapher calculators. I got the square root of x plus 1. And when I graph that, you can see that this has a domain that goes from -1 all the way to infinity, and it has a range that goes from 0 all the way up to positive infinity. And so you can also graph that on your own, the square root of x plus 1. The graph will be helpful in identifying your domain and range. Now, the domain and range of our inverse, this is going to be a little bit weird, right? The domain is now going to be these x values that go from 0 to infinity, and the range is going to be the y values such that they go from -1 to positive infinity. All right? So these changed. Now here's what's weird about that, because if we kind of think of the inverse as swapping just the x's and the y's as variables, I'm going from y is equal to the square root of x plus 1 to now I'm having x equals the square root of y plus 1, which is weird. So this is just a mechanism for us to figure out how to get the other variable by itself. I know it's a very, very strange approach, but basically here's what's happening. When I square both sides, I get x squared is equal to y plus 1, and then I subtract 1. So x squared minus 1 is equal to y. This function right here is a parabola. But the problem is that this parabola is not defined as the whole U-shaped parabola like usual. It is only half of that parabola because it's only the half that was defined in the original relation. All right? So here we have a situation where the original graph looked something like, and I'll draw it in blue, looked something like this. But then so this is f of x, right? The square root of x plus 1. But then the inverse is going to be like this. This is f negative 1, the inverse of f of x. And we should notice that if we're looking very closely that this is reflective over the line y equals x. All right, it reflects over that line y equals x. So even though we have this like kind of definition of what y would equal, it's only defined for the x values that are greater than or equal to 0 from this original range. That's going to be the limitations in our new domain. All right, so I know that's a little bit kooky, a little bit crazy. The idea here, we can still have a function, yes, but that function is only defined in limited capacity. So it's still a function, but it's a little bit weird. All right, so hopefully that's interesting to you. Hopefully that's neat and whatever. All right, we can do the same thing with a quadratic that we then invert to a square root. The problem is that when we take an actual full parabola and we reflect it over the line y equals x, or we find the inverse, we're going to have a positive and negative square root, which means we're not going to have a function here. So, spoiler alert, this is not going to be a function when we find the inverse. The domain of our original is going to be the x values that go for all real numbers, right? Negative infinity to positive infinity. The range, on the other hand, is going to go from negative infinity up to positive 4 inclusive. This parabola is an upside down, very narrow parabola, boop, that comes all the way up here to this maximum value of x is 0, y is 4. All right, but it'll go all the way to the left, it'll go all the way to the right, it'll go all the way down, but it'll only go that high. The inverse, we can picture what the inverse is going to look like. We know it's going to be very narrow again, but it's only going to go over as far as positive 4 on the x value. So the domain is now from negative infinity to positive 4, the original range, and the range is going to be from negative infinity to positive infinity. All right, so this is not a function, the inverse. But what is that handwriting? What is the actual inverse? So this is where things get a little bit kooky, obviously, because we want to be able to take our original function y is equal to negative 3x squared plus 4, and we want to swap the x with the y. Again, this is just a mechanism for us to understand, our mechanism for us to understand how inverting works. We're switching the elements in the domain with the elements of the range. Again, a little awkward. X minus 4 is equal to negative 3y squared. We're going to multiply both sides by negative 1/3, so we're going to get the opposite of x plus 4 all over 3 is equal to y. We can rewrite that as 4 minus x if we want to. So I'm going to write that as, squared, 4 minus x over 3, which means that y is going to equal the plus and minus square root of, it is minus x, of 4 minus x over 3. So we're going to have a positive output and a negative output for each of those inputs of x, which means it doesn't pass the vertical line test. We're going to have 2 outputs there. And so the goal here is, can we invert a function? Can we write that in reverse? Can we do the dang thing? And how will that be beneficial for our conversation about working with these relations in reverse? All right, so for example 5, what we're going to do is we're going to dig into some real world situations where we still go through the inverse operations, but we're not swapping the variables, right? That might make things a little more confusing. You might be like, so why were we doing that? Well, we're trying to get the model into a way that makes sense to our graphers and our mechanisms for graphing functions, all right? And so what we're going to do here is, with some real world connections, I know that this might be a struggle for us, but we're going to try to do this anyway. The goal with these real world problems is that we have enough information to kind of navigate this as best as we can. And so what we're doing here, the function d equals r squared over 24 is a model that shows the distance it takes for a car to stop depending on how fast it's going, the speed in r, the rate of speed. So finding the inverse, essentially what we're going to do is not swap variables. Instead, we're going to solve for the other one. And I know that sounds silly, but we're basically going to take, if d is equal to r squared over 24, then let's multiply both sides by 24 to get r squared, and then let's take the square root on both sides. Now there's a couple things that I'm going to ignore, all right? The first is, in this situation, the distance required to stop has to be bigger than or equal to 0. The rate has to be bigger than or equal to 0. So these are some assumptions that we're making about this real world situation. Now that doesn't mean, negative numbers, we only use those in math class. Like there's a place for those where that can signify direction that things are traveling. We're not going to be traveling in reverse, right? And so that's not really something that we need to be considering in this regard. We want to consider just those positive, or I'm sorry, non-negative values. So this will tell us, use the inverse to estimate the speed of a car that made skid marks this long. So essentially what we're going to do is we're going to find that rate is the square root of 24 times that distance that it took to slow down, which was, or to come to a complete stop, which was 114 feet. And so we'll be able to approximate r being, whoops, let's quit here, 24 times 114, that's the square root of 3456, which gives us approximately 58.8 miles per hour. All right, that was the rate that it was traveling. So think about that. If this is an accurate model, which I don't frankly know that it is, sounds about right. If you're going 60 miles an hour and you slam on your brakes, it's going to cause you to travel another 114 feet before you come to a complete stop. All right? And so that's why we want to make sure that we're always being vigilant when we are driving. All right, now here's the last little fun fact, and then we are going to be done. And that is the inverses, when composed, give you an output of x. All right? So if you have f and f negative 1 of x, and you compose them, you're going to get the output of just x. So that also means that f of the inverse of f of 2 is going to give us 2. And now let me kind of show you how this works. So this is a statement, this is a fun fact, this is reality, but let's go ahead and show what happens. We can use this to try to understand this situation. So if I do f of g of x, then I should get an output of x if these are inverses. So watch what happens here. When I put g of x in place of x, let's see what happens. I'm going to have f of 6x plus 7, which means I'm going to have 6x plus 7 in the numerator, and then I have minus 7 over 6. Now if I do that, then I have 6x plus 7 minus 7. These are going to cancel out. I'm going to be left with 6x over 6, which those then cancel out. I'm just left with x. So f of g of x is just x. These are inverses. Yes, they are. Over here, let's try that and let's see if that works as well. Hopefully you can look at this and say, ooh, the inverse of multiply is divide, and I'm not dividing. The inverse of subtract is add, and I'm not adding here. So these are not going to be inverses. But let's check that. F of g of x equals f of 4x squared, which means that I'm going to take the square root of 4x squared and then subtract 4, which means I'm going to get the square root of, well, that's not really going to work. I got 4 times x squared minus 1, which is going to be 4 times x plus 1 times x minus 1. I can't square root that. All right? Furthermore, I'm supposed to do well, I guess I don't have to do the plus or minus here. But the goal here, and the thing that we want to wonder about is, can I take that square root? And the fact of the matter is, it's not working out where the square root of this is going to give me x. So this is not inverses, not inverses. Now, one of the questions that I just heard in the back of my head is, f of g of x work? Does g of f of x work? Funny you should ask, right? This will equal x on this side over here. So what I want for you to try as I want for you to show that g of, using this over here, that g of f of x does equal x. I want you to show that it equals x. So that means you're going to do g of x minus 7 over 6. All right? So use that to see that you can show me that that output is x. All right? These are not inverses, so it didn't work. These are inverses, so it will work either way. Show me that you get an output of x on that one. And then that's the end. All right? So this is working with those inverses. I hope that you're feeling a little more comfortable with that. I know that word problems are a little bit of a mess, but we're going to navigate that very well.